Good afternoon, everyone, and welcome to Wavelogix Lunch and Learn. I'm Suzanne Florick, and I'll be your host today. Let's start with a quick intro to Wavelogix and today's speakers. Wavelogix was founded in 2021 in partnership with INDOT and Purdue University. Our goal, to help make roads and bridges more reliable and less disruptive to build. Our flagship product is the Rebel Concrete Strength Sensing System. It gives you real-time, in-place concrete strength data without needing maturity curves, and it works across all kinds of projects. That means better accuracy, better scheduling, and real savings. Now let me introduce Joe Turek, our president and our CEO. Joe earned his electrical engineering degree from University of Notre Dame and his MBA from Kellogg School of Northwestern. He has been in manufacturing his entire career, holds 5 patents in microwave telecommunications technology, and is a licensed professional engineer. Basically, he knows how to build things that work. And now, please meet Dr. Luna Liu, founder and CTO of Wavelogix, a true innovator reshaping how we think about concrete and infrastructure. She's not just an engineer, she's a trailblazer connecting civil, electrical, and material sciences to make roads, bridges, and buildings we rely on smarter and more sustainable. Her work includes everything from IoT sensors that talk to us about real-time concrete strength to next-generation materials that cut carbon and speed up construction. Dr. Liu has published over 150 scientific papers, holds more than 15 patents, and has earned a big-time recognition, including the NSF Career Award, ASCE Game Changer, and Alfred Nobel Prize, and even the 2024 Edison Award. And if that's not impressive enough, Purdue named her the most impactful faculty 3 years running. In short, if concrete could have a future-proof superhero, it would be our Dr. Liu. So, all right, Joe, let's dive in
All
and
right,
have a little
fantastic.
chat with Dr. Liu today, who we're so lucky to have on our webinar with us.
Luna, it's really great to have you. It's everybody's been wanting to talk to you. Few people have a chance to do it. We want to kind of delve into this. How does someone with your stature in that, how did you get into civil engineering?
Yeah, first of all, Joe and Suzanne, thank you for organizing this webinar. I appreciate the opportunity. Has been a great journey to work with both of you in the last 4 years. To answer your question, this has really come from the industry, right? So about 8 years ago, Indiana Department of Transportation has been long-term collaborator with me and Purdue University. Come to my office, say, hey, we have a problem, Dr. Liu. We want to know when we should be the right time to open the traffic for Interstate 65 after major repairing, like a patching job or building a new section. And as we all know, the very inconsistency of the cylinder testing, flexural beam testing that caused a lot of problem for the contractor, for the owners, for the designers. And then with maturity sensor, which is a leapfrog compared to the cylinder testing. However, you have to establish, the maturity curve, and then it's very hard to calibrate. So the request said, hey, can you develop something, measure real time and no pre-established calibration curve, it's not changing every time. So we started that journey about 8 years ago and, published almost, I forgot, 10, 20 papers along, giving a lot of talks, and started to develop the prototype product and went with INDOT on, several road application and all the other states such as Texas, California, Missouri, all Iowa, and started joining with the federal highway for what we call the pool fund program, right? So that leads to today, the inception of the Wavelogix. I'll
Yeah,
stop
so that
here
that
again,
so you're giving us kind of the end story. We want to go all the way back. What got you excited about getting into civil engineering? How did that happen?
So for two reasons, I think it's a scale and an impact, right? I think people do not give the, enough credit of the civil engineering to the truly we deserve. Honestly, concrete and civil engineering is very much the foundation for our modern civilization, right? So if you think about it, however, everybody excited about the new iPhone 17 Pro, nobody say, hey, thank you, civil engineer, you built these roads and bridges so I can drive safely get home today, right? So, but if you think about the impact and the scale, what civil engineering has been made ever since there is the human civilization, I think that's tremendous. So with that, and of course, there is also family impact as well, right? My dad is the entrepreneur, and he has a very small civil engineering firm. So he's a builder, right? He does deep foundation work. So I got involved from civil engineering very early stage. Other than being academic, before I went back to school to pursue my PhD degree, I was actually a civil engineer, assistant project manager for Kiwi construction at Miami International Airport. So I love
Wow.
build stuff, right? So I am the builder myself.
So that's an incredible story. So your father actually had a civil engineering company, and
Correct.
so how
Back
young were you when you started getting experience with civil engineering?
10 years old roughly, and two of my older brother work with him.
Oh
It's
my
it's
gosh.
sort of like family business, so it's a deep foundation work. So
Yeah.
piling, as you know, in the early um, 2000s, China was booming with the civil infrastructure work, right?
Wow.
So I
Now,
was
do you have a
very
picture of
involved.
yourself with a hard hat on at 10 years old?
I definitely have a picture of I myself driving, the big Caterpillar, um, all of the bigger equipment.
Oh my gosh, do
Yeah,
you really? That's great. Yeah,
yeah.
we're going to have
That's
to get that picture,
fascinating.
Sue, and share that with the world. Start early. That's your vision for all young girls. Now you have a daughter yourself. Are you going to get her into civil engineering?
She loves to build stuff, but at this point, it's just the Legos.
I was going to say, how many Lego sets have you had in a lifetime?
Yeah, yeah, a lot for sure. Yeah.
That's fantastic. That's great. Uh, and you've done an amazing job at Purdue University and put your mark on that. I'm an electrical engineer, and I think I've told you many times, had I known that civil existed, I probably would have gone into that field. But at Notre Dame, the civil engineers were the guys with just the little tripods and the little scopes, and they were always just measuring levels in that. I had no breadth of that. Now, my wife is a materials engineer, and she always told me that was the basis of everything. I'm like, you're just playing with rocks. Little did I know I would swing around into being more of a civil engineer than I am an electrical engineer. So that's really cool. Now, did you have any idea when INDOT came to you with their problem of how to attack it? Had you had an inkling? What what was the brilliant light bulb that went off and you said, this is how I'm gonna make a new sensor to measure concrete non-destructively, concrete strength.
And how long
Yeah,
did it take you to come up with the whole I'm so intrigued by innovation, and to me, like learning how to innovate, how your mind worked during that period of time is super interesting.
yeah, fantastic question. So I'll start to answer Joe's question and then went to on the journey. So when INDOT asked us to develop the methods, of course, we're tinkling around a couple of different things, but one thing really come to my mind is how we're doing non-destructive testing in electrical engineering field and aerospace engineering. If you think about it, right, all the Boeing 787 or Dreamliner, all of this, it's really using piezoelectric, right, non-destructive sensor to measure the integrity of the airplane, right? The
Right,
same thing with
right.
your circuit board. Joe, you work on the circuit
Yep,
board for years, right? So how
yep.
you measure that, it really sends the wave and then looking at how wave propagates through it. So that has always been, the starting, that's the physics, right? So
And
to
you were working with this technology in your lab already,
correct.
right?
Correct. I've been working with piezoelectric technology for years. As a matter of fact, part of my NSF career proposal, which is really, recognize the younger leader in the field was in that area. So I immediately made that connection. I said, hey, why not integrate it in the piezoelectric sensor into civil engineering field, right? That being
Yeah,
said, the challenge it really lies in concrete is not a homogeneous material such as aluminum, such as the steel, right? It's very much a composite. You have aggregates, you have your sand, you have your water, you have your air, you have your cement. Your cement is different, your aggregates is different. That can be, the limestone, that can be anything, right? That can be
everything.
lightweight aggregates. So there's so many varieties. So that caused the challenge. So the physics is straightforward. However, develop that engineering principle and the mathematic foundation that takes almost 3 years, right? So work out all those details. And then in the last 4 years, we developed a prototype, right? Build the product and iterate the product, right? So with the dashboard, and so I think now we have a very complete solution end to end. That
Yeah,
basically you just then need to plug in the data sensor and the sensor and data logger, 5 seconds, boom, you get the solution. So
yeah,
that the entire journey now, I think almost a decade, right?
yeah,
8 to 9
It's
years. Yeah.
yeah, 9 years. That's amazing. And what I find very elegant is it's a beautiful solution that uses the physics of a structure, the physics of a solid, and
Yep.
not just like maturity sensors, nothing more. I mean, there was no brilliant science and invention in sticking a temperature probe into concrete and measuring its hydration, curve, right? I
Yep.
mean, your product, your concept really, I think, was interesting because it doesn't matter how old the concrete is, right? The
Yep.
sensor could measure it 20 years from now if we wanted to.
Yeah,
Yeah,
yeah. So if I can comment on that very quickly, Joe, I think you do raise the very important point, right? So this sensor fundamentally different than maturity sensor because in principle, maturity does not measure strength
hmm,
or mechanical property. In principle, maturity measure temperature, as you pointed out, and
yeah,
correlating temperature to hydration.
hmm,
There is the fundamental challenge is number one, temperature is only indicating hydration, which is only happening at the very early age of the concrete
yeah,
mixing, right? So typically 24 hours, 48 hours. It depends on, your water cement ratio, your mix design.
yeah,
However, after that, temperature become a plateauing, right? So you can only, if you do a very good job of calibrating,
hmm,
and you can only do a very good job on the very early beginning, but you cannot measure like, accurately for 7 days, 14 days, 28 days,
yeah,
or so on and so forth. That's number one challenge. So in
yeah,
contrast, what we do, so when I started doing this project, I said, first of all, I don't want correlating anything like a temperature, the moisture, right? If
you
we
didn't want to have any
truly
type of calibration, right?
exactly, exactly. If we truly interested in mechanical property, which is in this case compression strength, why not we measure mechanical property, right? So
Right.
what is a true mechanical property for any material is modulus, right?
Hmm,
It's a stiffness. Anybody, if you're a civil engineer, you're a PE, you're a designer, you don't design by compression strength, you design by modulus. So why
hmm,
not we go by measure modulus? Because modulus is independent of the sample size, independent, of many other geometry factor, right?
right.
So that's how we started. To your point, this is really physics based because in physics, what you can measure is modulus. And then we use the sensor to measure modulus. And then we use the machine learning and AI to guide that, make a decision, right, to the
Yeah,
compression strength.
yeah. Beautiful. Well, it seems like it's worked out well. You've got a device that doesn't require calibration and it can go the distance, 28 days or 28 years, as we like to say.
Yep.
Yeah. Now, the biggest challenge that I think you faced is getting people to actually try it and put it into an actual program, right? What's the thinking behind that process? How do we get someone to, actually give it a try and what's your thoughts on that?
Yeah, that's a great point, Joe. I think, civil engineering industry, like many other industry, perhaps even a little bit more, it's very risk, conservative, right? A very
Yeah.
conservative, risk adverse. I think this is by training, everything put a 2x, 3x safety factor, right? So getting people to try it, it has been a biggest challenge. However, at this point, I think in the last 5, 6 years, with all the support from Department of the Transportation, from the industry, we have had quite a bit of the pilot programs, right? Joe, maybe have over
Yeah.
35 states has participated in this. So trying this is it's quite a straightforward process, right? So you started your pilot programs as you clearly laid out here. And then, getting some of the testing kits from Wavelogix, and then you can just directly put it in the concrete and then, pour concrete on top of it.
Yeah,
Yeah. So
that's pretty good.
Joe, maybe
Yeah.
maybe you can get, more in depth about the process,
No,
what I look into it.
I think that's, you know, that's really a perfect way of doing it, right? You're trying to get a program going. You start with first you buy a kit and then you start with a pilot program and then you kind of step it through. I think some of the things that we have seen, if we were just to kind of lay it out was, you define the scope, right?
Yep.
Um, that's sometimes is the hardest thing, right? You've worked a lot with NDOT and the other dots around the country in that, right? Just getting a scope so that they do a proper test and not just throw the sensor in the ground and go, oh, we did this test, right?
Yeah.
So so that kind of works out well. You kind of get a team together. If you don't have the right people who are going to spearhead it, you're not out there in the field showing people how to use it. It's a very simple device, but if you don't have the support of the people who are going to do it, that's not going to work, right?
Yeah. Yeah.
um, and I, we train and deploy. Now, one of the things that you helped develop was a very concise um, dashboard for showing the data and an onboarding session. We almost have a plug and play product, right? I mean, you talk a lot about you drop a sensor on the ground, you pour the concrete on it, and boom, you're reading strength automatically onto the dashboard. You plug it into the data logger, and you don't have to do anything else, right? It
Yep.
just starts working, which is really nice. You don't have to go back and refer to a conversion chart or plug in some calibration chart. It's just giving you strength for as long as you keep that data logger plugged in or whatever, you come back and plug it back in, right?
Yeah.
Um, a
Hey,
very
Joe,
nice, elegant solution.
Joe and Luna, what evidence gives you the confidence that the data is decision grade? What is it that shows if somebody's doing this in a pilot program? Because everybody keeps going back to, cylinder brakes, but how do you feel really good inside that the data you're getting is decision grade data?
Luna, any thoughts on that?
Yeah, I can say, so from our experience, in generally, we want to do two things, right? And number one, it's, the lab control the cylinder testing. So the cylinder has been very inconsistent. It's basically depends on who made it, right? How you
Mhm.
make it, how you cure it, how you transfer it. But if there is one ACI certificated technician who make the cylinder meticulously, right, cured as what they instructed, and tested as ACI, or ASTM C39 standard, and then you typically get consistent results, right? So that's what industry looking for compared to the cylinder testing. Some
Mhm.
states they do a core drill, right? So for example, Indiana does core drill testing, and then looking at the real in place strengths that can compare to our data, and then very comparable as well, right? So we are roughly about 10% within that pretty tight band region, right? Again, concrete is composites material, you cannot expecting this cylinder exactly the same as next, right? So roughly people looking at it from industry, from ASTM C39 standpoint, is about 15% within 3 cylinders, right? So we're very much within that range or even tighter, so our data. Joe,
Yeah.
would you
So
like to
a
add
lot.
on? Yeah.
Yeah, I mean, we have probably 10,000 pours that we have done to validate the data against cylinder breaks. And so it's a pretty well-established database, if you will. And we have data that spans every type of concrete from 500 psi up to 20,000 psi, and it's all about collecting the data and then using today's, I think, AI models that help discern the information to give us something that's really strong. I think analyzing those results is really a key, getting that done, and then driving consensus after you do that. So you bring up a good point. Does do people believe what they're seeing? The one nice thing about our sensor is that it's like a third party QC device or QA device. You can't fake the data. You can't fake the output. On a thermocouple with a maturity sensor, you could change the temperature theoretically. You could kind of fake that output. You can't change the output in our sensor. It's buried in the concrete. It's going to read what it reads. Also, you can't it's not dependent on how someone puts the sensor down in the ground compared to like cylinder brakes or beam brakes, like you said, Luna. That has human interaction. That has a lot of variability because every individual who makes a cylinder or beam might make it slightly different. How many times they pound it with the rod, how they convert it, how they carry it, where it's stored until it gels, when it gets brought back to the lab. There's so many variables in there that you start to really question whether or not cylinders and beams are really the accurate way to measure strength. And yet, what do you always say? We've been doing that for over a century. It's an archaic method, probably been doing it since the Roman times, right? To really determine strength. So that's really important. And our process of educating the customers as well is really important to continue to get support from us. We should probably just share. You and I had a chance to go to our favorite city, Fort Wayne, and we had Brad on, I think, in our last webinar. So didn't we?
We did.
Yeah.
And part of the reason why I was hoping you might bring this project up, Joe, is because what they did a really great job of was documenting their pilot program.
Yeah.
So that they were then able to show it to their team in order to what was on the last slide you had, which was build consensus within the municipality of Fort Wayne. And it wasn't just being kept in the QC division or with a group of civil engineers. They've been able to show this to people to really build consensus and have high expectations of using our sensors moving forward in Fort Wayne in order to help build their constituents' happiness levels of opening their streets on time.
Yeah.
So this is a great example of what they did. So
let's just show this off a
let's
little
take
bit.
a
You're
look
right.
at it, Joe.
Yeah, it's really cool. Now these guys, all we did was an onboarding session with them and train them, over the web on how to deploy our sensors and what to do. And then they went off and ran their project, and they came up with some innovative things. And this is a normal city street that they have concrete on. And understand that when they do a city street, guess what? All these people with their garages and their cars can't ride on this road. So they are super anxious to get these roads open as fast as possible. So, what do they normally do? They prepare the road, right? They rip up the road, they put the forms down. Here on the left is what they had to set up, what they typically do then for their project. Of course, they've got an air meter in there where they're going to look at the amount of air in the product. They're setting up their forms for the beam brakes and their cylinders. They did both cylinders and beams for this particular project. And here's what they had to do for the Wavelogix sensor on the right. You just drop them on the ground, bring the cables out, and then they bring them to the data loggers in the little box. Easy, simple, lightweight. Brad made a comment that, one of the things about getting women, Luna, you'd appreciate this, women civil engineers into the field is that trying to carry one of these beams, these things are like 80 pounds a piece. I
Yeah.
can't carry these. Yeah, I mean, so it's limited to big burly guys who can carry these cylinders and beams back and forth in the truck. It's a lot of heavy work. Brad was saying, boy, we can now go out and hire a bunch of interns, and it wouldn't matter if they're male or female because it's easy to deploy. So that was kind of a cool little sideline that I liked. They also had an interesting aspect of their project, which we don't think about. We haven't thought about when on most construction sites on roads and big projects, people are limited for access to those sites. Not in your local community. The folks are still walking their dogs down the sidewalks, and they were concerned with having this little data logger, our data logger, sitting outside on the grass, that it might be stolen or damaged or someone might unplug it. So they created a box which it allows us now to sell. And so we have this product that's available to everybody. To put the data logger inside of a box, it can be screwed into the ground. It gets locked. It can be strapped then around a tree, which is what they did. And a big warning label on here that you're going to go to prison for 100 years if you touch this box. So it's really a kind of a cool device and a great way of doing it. They innovated that. Now here's the results, which are great. I mean, this is highlighting exactly what you were saying, Luna. They took our sensor data, and you can see the sensors are the solid black lines. The red dots are their cylinder brakes, and the green dots are their beam brakes. And the beams were converted from flex into compressive strength on a 10-to-1 ratio. What I find most interesting is look at the range that you see in their beam brakes and their cylinders, all made at the same time, all broken at the same time. There is a huge variability. Now, there's some variability in our sensors from sensor to sensor, but much tighter. Their next slide, they average the data together, and on average, this is what you'd like to see. That all the data kind of comes together. So from what you were talking about and you were asking, Sue, is how do you validate some of that data? And they validated it in this case against beams and cylinders. And the industry standard is averaging the data, right? Because of the variability, then let's average it and kind of take that average. And you can see a very tight correlation between our sensors and their averages of their product. The next slide now shows what the min-max was of those cylinders and the sensors and the beams. And as you would guess, the beams have the widest variation. And you can see that very wide scope. The green lines represent the cylinder brakes. Again, pretty wide, but within industry standards. We're seeing about 1,000 PSI variation. And then when you look at the variation in our sensors, from high to low, the tightest of all three of them, down around 500 to 600 PSI. And our data, of course, variation falls within all of this. So, suffice it to say, Brad in this, process and experiment was really impressed with the results of this. And that's what they were hoping to see, and that's what they had seen.
Joe, before you move on, maybe I
Sure.
can also want highlight one thing,
Sure.
looking at this data for the red curve, the beam, or the green curve or the cylinder, clearly you have seen a big dip of the curve, right? With the time goes by, what you're expecting is the strength development, right? Going up, it's not going down. So this is again going back to our point. If you only use a beam or a cylinder as your decision-making tool, it's completely unreliable, right? How come you get 5 days strength is way lower than your 3 days, and then your 7 days is jump again? It depends. It's purely depends on luck, right?
Yeah.
And versus the rival sensor is consistently increasing, right? With the time goes by and you see a larger increase and then started steadily develop the strengths, right? So I think this is, again, very much follow the physics, right? Very much follow the nature of the product. Yeah.
Yeah. So
Can
extremely
I
good
ask?
point. Sure, go
Yeah.
ahead.
Can I ask you both a question? So when you see a presentation like this, it's very clear that our product works. And so when you're in a pilot, what is the biggest adoption blocker that you guys have seen, and how do the people running the pilot program remove that blocker of getting the product adopted and into operations?
Joe, you want to start since you're
No, go ahead, Luna. Yeah.
Oh, no, I can speak
Okay.
a little
Yeah,
bit
sure.
about my experience early stage
Yeah,
working with Department of the Transportation, right? So
right.
as you pointed out later on, I more taking on the CTO role rather than driving the operation. So early with the Department of the Transportation, I think, there's so many of very friendly, great transportation groups, such as again, Indiana, Iowa, and Colorado, and Texas, right? So California, and we work with them, pick up the right scope to Joe's point. That can be a bridge work, that can be pavement, right? That can be, the retaining wall. And I think the getting into the biggest challenge, again, we want to say, that, again, first of all, thanks to all 50 states. Thanks for your support. We have an AASHTO standard, which is a national standard, right? So this is with all states' support. And then once that standard is established, the biggest challenge is getting into the specifications. So each state have a different specification process, different specification committee, right? So that process can be lengthy. But luckily, and I think this is also very quick consider of civil engineering technology adoption speed that we're already in the specification of the state of Massachusetts, right? So we are in, I think, at the very later stage with two states, two very prominent states, and potentially, I think very likely will work us in their larger leading concrete state in this year.
Yeah. So it's yeah, I mean, you've really started a revolution, Luna. I mean, and we have a subtext in our Wavelogix Rebel that says break free, right? I mean,
Yep.
your ultimate goal when you first enticed me to join the company was, your vision was to eliminate cylinder breaks altogether, breaking
Yep.
free from the
Yep.
tyranny of 100-year-old technology that is, that we've been bound to, that is, shown to be totally inefficient and ineffective.
And
And
everybody
yet we
complaining about it create a lot of waste of the
and
cylinders, concrete. Yeah.
nobody has done anything with it. Now, what I'm really impressed with is how well and how fast the industry has started to adopt and use
Yep.
the product, right? I mean, this industry takes forever. When we talked to Minnesota DOT, they said it's taken 6 years to get a microwave oven approved to be used in their process. I mean, it is agonizing. Watching paint dry is faster than the construction industry moves. But you took 6 years in the lab to perfect the product, and then you did 1 year of field trials, and within 6 months you had an AASHTO certification, and the next year we have had over 250 projects that are being done, over 1,500 sensors that have been deployed in those projects, 34 states across the country. We have projects in both government and non-governmental. We started, and your vision started, and with the help of INDOT DOT. So it was focused on bridges, paving, and patchwork, but yet the product now has expanded into so many other areas. We're into a precast,
Yep.
ready mix companies, contractors are using it, RCC, roll compressed concrete. We have tremendous different success stories in each one of them. I mean, I was talking with Amrise the other day, and they said, I said, how do you like our sensor? And he said, well, let me tell you, the one thing we love about it is it doesn't have to require calibration. We were ready for one day going out to the site, and the customer changed the mix design. And we said, they said, you have to deploy this new mix tomorrow. We need to stay on schedule. And they said, but we don't have our maturity curve done. We have to go back and wait 7 days to at least, define the maturity curve. And our customer said, but wait a minute, we saved the day. We got these Rebel sensors that we could deploy immediately because they don't require calibration. And they deployed them, and the project worked out great and stayed on schedule. We see that precast, who's trying to improve their schedules, when to open their molds, when to release the tension and pre-stress, all is time dependent. And when you're developing strength on precast and with patchwork, you can get to 3,000 psi in 6 hours, right?
Yep.
I mean, that you could watch that harden almost immediately. But try and get a cylinder and breaking it and getting that data in a timely fashion. By the time you've broken it, it's already increased by 500 psi.
True.
So things move very rapidly when we deal with some of these, quick drying, quick curing concretes. That having a sensor in real time is huge, right?
Yep.
So that's really cool. So I mean, I think this revolution is really starting to take, develop and harden as it grows, and it's probably an adoption rate and a use faster than we have seen ever in almost any product in the construction industry. And I think that goes back to your genius in coming up with something that is so sorely needed. There's nothing else like it on the marketplace, and it is a vision and a means for us to eliminate cylinder breaks. And that's really the holy grail for us, right? We have 3 counties so far that have adopted, across the country, that have adopted eliminating cylinder breaks. And I think that was the original vision in Indiana and other state DOTs, to be able to use this and eliminate cylinder breaks altogether. Having a product that's as good as an independent third-party test lab that can't be modified, easy to deploy, that it can be deployed by the contractors, or easier deployed and optimize the workforce in DOTs and anybody who does QC, and give us accurate and real-time results. I think you've done a wonderful job in that vision.
Yeah, I appreciate that, Joe. I think you're very kind to say that, but I do want to mention 2 things. Number one, it's industry buy-in. It's so key, right? It's very critical. I really appreciate, the DOT support, not just from Indiana. It's really from the nation, the community, and the contractors, right? So when we first developed the prototype and giving to the contractor that milestone, I remember. So the Steve Freeze, the vice president of Milestone, said, "Hey, when I can have a real product, Dr. Lu, everybody hates the beams and it just hurt the back, right?" So there's a lot of problem with that inconsistent, and every single beam represent $50,000 the day of the work. If that beam data is not right, there is argument, litigation, right? So there's so much a problem. They say, "Hey, let's have something." Number one, industry buy-in. I really appreciated all the industry partners, right? The DOT, and thank you all. And having that. Number two is, let's talk about moment about why we want to get rid of the cylinder testing. It's not just because it's 100 years old, but really because of that inconsistency drive a lot of problem in our industry, right? So we now have to add 25% more cement in our mix. So to make sure we're compensated that inconsistency, right? Everybody know if I get a bad breaks, and then I have to pay more money to fix it. So why not I put 25% more cement? Number one, you waste a lot of material. Number two, cement is the most expensive thing in the concrete. Like, right? So you add a lot of the cost to the contractor, to the owners. Number three, which is the biggest issue, we're not talking about it. Because of that 25% of more cement causing more durability issue. Now people complaining, oh, there's an early age cracks, there's bleeding, there is scaling. Why? Because you add more cement, more than what's needed. There is not enough water, not enough other material to reacting, right? You're basically against the physics. So therefore, we have waste more material, build a worse product. You know, that's the fundamental challenge of the cylinder testing. We need to get rid of that inconsistent testing. And I'm really happy we are part of this equation. Again, thank you, Joe. Thank you, Suzanne, to join the company, right? And I believe because of this, you see the bigger challenge we're facing in our society. We're addressing this. And I did not take you much of the to decide to help to contribute, although this is a very risky journey. And I still, you know, and thanks to all the industry partners, and also hope as a professor teaching in the largest civil engineering program in the nation. You know, Purdue Civil is the highest ranking, right, #2 in the nation, and then we're largest program. And I was also previous department head, and I really hope we can contribute something to our society to address this problem. Again, I want to say concrete. It's the largest single-used material in the world, right? If we can reduce 25% oversubscription of the cement, what is the contribution we make to the society as all the civil engineering join this webinar and in this community? I do urge you, please take the opportunity to do one pilot testing and tell us if this is good or not, and how can we further improve. And thank you to be a great partner.
Well,
Yay, all right,
Dr.
that's
Liu,
the
I
bell,
think
Dr.
that was a great closing statement. And I'd like
Love
to
that.
also just add to you that I find I-65 a tremendously trying highway to drive up and down due to all the construction. I myself am a Kelley School of Indiana University graduate, and I've driven up I-65 for so many years. And to watch now that the past 10 years that you've been partnered with INDOT and Purdue University to help solve the problem with them and increase ROI in all civil engineering projects across the country is a tremendous effort, and well done on your part.
Thank you.
Absolutely.
Thank you,
And
Suzanne. I do see there is a question in the chat, so
yeah,
maybe we'll
but
take
I
a
want just one last comment I want to say, and then we'll go to the questions. But Suzanne and I did not join your company. We joined the revolution, Luna,
of
and
it.
we're hoping everybody else joins this revolution to free
Of it.
us from the tyranny of cylinder brakes and beam brakes. So
Yeah,
let's go to the
yeah.
questions.
Thank you.
So,
Thank you.
so
Thank
we
you.
have one question here. In practice, the space of possible concrete mixes is enormous. Various aggregates, mixtures, SCMs, curing regimes, fiber reinforcement, etc. Has the sensor been tested in various concrete mixes? And what is the confidence level and uncertainty of the sensor readings?
Yeah, this is a fantastic question. Thank you, Hamid, to raise this question. You know, this is actually fundamentally why we don't want to develop another maturity sensor, right? Because how can you do the calibration for all the different mixes, the different material suppliers? To answer your question, yes, absolutely, yes. So in the last 6-7 years, we tested with various concrete mix design. Joe perhaps can give you the specific number, I think over thousands. You know, just thinking about it, 35 states has using it, right? Over 200 different projects. We tested the water cement ratio ranging from 0.32 to 0.65, right? So a wide range. Of course, as you can see, the open traffic, you know, precast to the later residential commercial work. And then for the aggregates, we have tested, you know, anywhere from the nation into the typical, you know, gravels and to your lightweight aggregates, even some area you have ASR, right? You know, alkaline silica reaction, right, with the very weak aggregates. And SCM, natural pozzoline, we tested, right, fly ash, silica film, again, geopolymer even. So all the different mix. Mean Road, perhaps some of you sitting here, you know, Mean Road is the largest trial pilot. They test all the different mixes, and we were part of the Mean Road program as well. So SCM for sure, and the fiber reinforcement, yes, you know, steel fiber, polymer fiber, you know, we can give you all the data. So roughly, I would say say on average, Joe said, talk about the average, we're about 10%, right? So the confidence level is pretty high, 90% confidence level. And we even tested on the roller compact concrete, right? So about 4-inch lift, things like that. So variety of the data, and we can provide as a very strong evidence. Again, it's really the leveraging of the last 6-7 years with industry support and also the power of the AI and machine learning, right?
Mhm.
Joe, you want to add more? I'll stop.
Oh, I think that's a number one question that we get asked is, and what blows people's minds is really, how can you be mixed design agnostic, right?
Yep.
Because we're so used to, basically looking at a temperature probe and measuring the temperature of hydration as our fallback to compression brake. But, the thing to remember is that, that mixed design is going to ultimately end up creating a structure that has a modulus. And
Yep.
our device is looking and reading that modulus. So it doesn't matter how you change and vary that mixed design, it's ultimately going to have some modulus, and we are giving you what that true modulus is. And so, and one of the nice things is we tested this across the country from north to south to east to west, because we know that a major element in strength in any mixed design is the aggregate of where it's mined from, and that's all local.
Yep.
Cement is pretty moved around the country, moved around the world. Water is water, sand is sand, but aggregate is one of the key things, that's going to be different. Even if you had the same mix design, even if you said this size and, and this weight, it's going to be different from where it is around the country. So that's really critical. And what we've in so many different applications in different areas around the country is that our product is really mixed design agnostic, and it doesn't require calibration. Now, there are some variables into that. We won't go into that here, but it is a unique process that is, part of the what makes this such an interesting invention.
Well, I think that's a wrap for today. Dr. Liu, thank you very much for joining Joe and myself on our Lunch and Learn.
That was great. Now we know what it's like to be a student in one of your classrooms. Wow,
Yeah.
that's exciting. I'm going to go back to school just to have you teach
Definitely,
us. Yeah,
definitely.
I'm taking new PhD students. Joe, you may apply.
Okay.
PhD.
I'm sure
Civil
any of your
engineering.
students who might be watching this or will watch this are going to just go, "Oh my God, a flashback. Oh man, I remember those lectures."
Exactly.
So,
Well, to all of our guests today, thank you so much for joining us. We hope we're leaving you with a clear picture of how the Rebel sensor can make your projects faster, safer, and more cost effective, which is super important. If you'd like to explore a pilot or learn how Rebel could work for you, please reach out to us at sales@wavelogic.tech or use the link on our website, and we'd be happy to have a conversation with you. And thanks for joining us and being a part of the future of concrete.
Thank you.
Thanks. Bye-bye.
bye all.
Bye.